So can anybody tell me what I can do? What's the strategy for figuring out if something is growing exponentially?
Multiplication.
Okay. So I heard a couple of things. First of all, multiplication. We know that exponential functions, they grow by multiplying. It's all about multiplication.
Miss, but don't you have to do the reverse to find out if it's exponential?
Yeah, I was just going to say. So, yeah, but in order to figure out if something is multiplying, we have to do the reverse, which is what?
Division. We have to divide everything.
We got to divide. So, how do I divide? Do I go from top to bottom or from bottom to top?
Bottom to the top.
Bottom
to the top.
Good. So we start with the bottom number and divide, and then see what you get, write it down, and then do the next two, see what you get, write it down, and then keep going from there. So what do you get when you divide the bottom one and then the next?
1.1.
We get 1.1. How about the next two?
1.1.
Again, right? 1.1. Do you always get 1.1?
Yes.
Yes, sure do. So very, very simple, very, very simple. As long as you have a calculator, you can do this without a problem. You just take the bottom two and make sure when you divide, when you plug that into your calculator, you're plugging in 87,846 divided by 79,860. Okay, so it's the bottom one divided by the next one up. And if you do that all the way down, you'll notice you always get 1.1. You get 1.1 and 1.1 and 1.1. So what is that number called? What is that?
Irrational.
It's rational, but in an exponential function.
It's also a constant.
Good, but it's a very specific. It's not a constant rate of change. It's a constant what?
Exponential function.
Constant factor.
There it is, factor. So very careful to know the difference between a constant rate of change and then a constant factor, because constant factor is when we multiply. So the constant factor is 1.1. Look at population of country B. What's going on in that one?
It's a constant change.
Constant what?
Rate of change.
Rate of change. Because what is happening in country B?
It's adding.
Adding.
5,000 every year.
Good. Plus 5,000, plus 5,000, plus 5,000, and so on. So that is a constant rate of change because it's adding. So just always be very careful because they both are constant, right? Because it's the same exact thing over and over again. One of them you multiply, that's your factor. One of them you add or subtract, that's your rate of change. So long story short, we know that country A is growing exponentially. And what about country B? What type of function does that one follow? It's not exponential. What is it?
Linear.
It's good, Bianca, linear. Linear. And that's the big difference. Linear, we add and subtract. Exponential, we multiply. And when you multiply, when you're dividing from the bottom to the top and you get the same number every single time, that number is your constant factor. Or it's also called the growth rate. Do I have any questions on how to figure out if something is exponential versus linear? Any questions at all? Okay, there is one homework assignment on this exact strategy. Already there's an assignment that I put yesterday on Khan Academy. So if you already did it, great. If you haven't done it yet, then this is exactly what it's about. So if you kind of need another review, you can always rewatch the class recording or watch the video on Khan Academy and see if you can go from there. But today what we're actually going to be doing is we are going to be graphing these types of functions. Yesterday, we spent a lot of time understanding what they are, how they work, what they kind of look like. Well, today we're actually going to be graphing them. And what I want you guys to do all throughout today, because you guys know it's a little bit hard to graph things in your notebook, but something that's going to be very important today is that you sketch the graph. So I'll kind of talk about how to do that in your notebook a little bit later. But before we get into it, let's just begin by reviewing one more time how to write an exponential function. We kind of talked about this yesterday a little bit, but we didn't spend a whole lot of time on it. So I just wanted to review this one more time. And you can go ahead and write down this equation right here, which is the standard form of exponential functions. When we write an exponential function, they're pretty much always going to look like this. And I'm just going to go ahead and label them because A and B represent two different things. Does anybody happen to remember from yesterday? What does A represent? Or
A
what does B?
intercept and B represents the growth factor.
Yeah, good. So A represents the y-intercept. And then B represents the growth rate or factor. Okay. So whenever you have a table or even a graph, which you'll see in a little bit, you can take a look at the table and we can figure out the y-intercept and we can also figure out the growth rate. So let's start off. We know how to do the growth rate now. Can anybody remind me once again, what am I doing to figure out the growth rate?
Dividing.
Divide, good, from bottom up. So go ahead and divide a couple of times and then see if you keep getting the same number. All right, so what do I get when I divide 1.8 divided by 3?
0.6.
0.6. What about 3 divided by 5?
0.6.
And 5 divided by 8.3?
0.6025.
Good. And it's not 100% perfect, but when you round to the nearest tenth, you always end up getting 0.6. So that is my growth factor. That is what I get. So what that's telling me is that when you go down, the pattern is multiplying times 0.6. And you can double check. If you want to double check now, what you can do is you go from the top and you take 13.9 times 0.6 and see if you get 8.3. 8.3 times 0.6, see if you get 5. 5 times 0.6 should give you 3, and so on. So I know my growth rate. All right, what about the y-intercept?
0.6.
Well, that's the growth rate.
Oh,
How do I find the y-intercept on this table?
the y-intercept is 5 because there's a 0 for x.
Good. Wherever x equals 0, that is always your y-intercept. So right here, that is my y-intercept. You can always find it on a table just by looking at the place where x is 0. So now I have everything I need. I know that my A is 5, my B is 0.6, and now I can write my function. So my function would be f of x equals 5 times 0.6. And you can either they use a dot in this example, but you can also use parentheses because both of those mean the same thing. We're multiplying. And then the exponent is my x, so to the power of x. And that is my function for this table. And you can do that with any table at all. all you have to do is find the growth rate by dividing from the bottom up, look for the y-intercept by identifying the 0, then that's all you need. You have your A, you have your B, you can write the function. So do I have any questions on how to write that equation or how to find any of those two values? All right, so now that we have one example, I want you guys to try it on your own on the next slide. So does anybody need a couple more seconds to write anything down?
Yes.
Okay, take a moment. All right, I'm going to move on in about 10 seconds. Alrighty, so let's go ahead and try another one. Very similar. Go ahead and take a look at this table and let's do the same exact thing. Figure out what is the growth rate, figure out what is the y-intercept, and then we're gonna write the function. And I'm just gonna write the standard form up here so that we remember how it goes. So take about one more minute to identify those two values. I know that they're big numbers, so just be careful when you type those into your calculator. It's okay, Shara, you're good. Let's go ahead actually now and let's look at it together. So growth rate, I'm dividing from bottom to top. So what do you get when you divide 19,144 divided by 18,233?
1.04.
Are there more decimals?
Yeah, no, 1.04.
Yeah, but that's why I rounded it up to 1.05.
So when you divide, you get 1.0499, right? 99. So I'm going to leave it like that for now because I want to do it one more time and see what I get the next time around. So this time, 18,233 divided by 17,364. What do you get that time?
1.05.
Mm-hmm. 1.0500. So the one that we did the first time around, I'm going to round that to the nearest. What's that for? What place is that for on?
Ones, I believe.
It's not the ones.
Tenths.
Think about money. Think about it like money. What usually goes in that spot?
Cents.
Exactly. And so how many pennies, because that's your pennies, how many pennies go into $1?
100.
100.
So that's the hundredths.
Hundreds place.
Yeah. Hundredths. So that's my hundredths plates. That's what I'm going to round onto. And so should I be rounding up or should I keep it as a 4?
Round up.
Up. Good. So this is 1.05. And that's what we get the next time around, right? We also get 1.05 when you round to the nearest hundredths place. So if I continue that and I keep doing it over and over again, I should be getting the same exact number each and every time, which means that my growth rate is 1.05. Okay. And then what about my y-intercept?
15,000.
15,000, good. You just take a look at where the 0 is, and there it is. That is my y-intercept. So A is 15,000, B is 1.05. So I go ahead and I can write my function f of x equals 15,000 times 1.05 to the power of x. Cool. How do we feel? Any questions on writing that function or finding those values? Awesome. All right. So kind of what I was saying before, right now we were looking at some tables. Now we're going to transition. We're going to look at graphs instead. And when we are graphing, what I need you guys to do is in your notebook, you're going to write down the function. So everybody's going to copy down the function, copy down the table for sure. It's going to be kind of a lot of writing today, but that's okay. We'll take time if we need it. And then we're going to be writing a lot of work down in this area. You're going to write all of that down as well. I want to make sure that we're writing things down today because the math and the work that we're doing, it's going to be very important that we're neat and organized in writing it down. Then when we actually graph it, because that's going to be the last step, when we actually graph it, you don't need to write this whole graph, like, you know how there's all the little lines in between and the little grids and everything like that. You don't need to write all of that down, but what you can do is a sketch. So a sketch would look like, let me see if I can put in a little blank page. Hold on. Okay. A sketch would look like this, where you would just do the y-axis and the x-axis, and then like 1, 2, 3, 4, 5 lines going up, and 1, 2, 3, 4, 5 lines going to the right. So that's what a sketch would look like. And that's what I want you guys to do in your notebooks so that you can have an idea of what this graph is supposed to look like. That way, when you have it in your notebook, you can look back on it and remind yourself of how it was when you did it in class. I know that usually we don't graph things in class because it's a little hard to do that, but it's going to be pretty important to do it today because we're going to be talking about patterns and what the shape looks like. And I just want to make sure that you have all of that in your notebook. So with all that being said, let's go ahead and just begin by taking a look at what we have here. So I have a function equation, just like the one we wrote in the previous slide, but something's a little bit different about it. What is kind of missing?
The y, no, yes, the y-intercepts.
Good, the y-intercept, because remember that usually you should have a times b to the power of x. So there's no a there, but let's actually think about why we don't see the a. Whenever there's a number that's like not there, it's kind of invisible, what is that usually going to be?
1.
1.
A 1, exactly. So I can kind of rewrite this. I could rewrite it as f of x equals 1 times 2 to the power of x. So now I know what is my y-intercept.
1.
Good. My y-intercept is 1, and my growth rate is 2. Okay, that's great because I can actually put my y-intercept onto my table right away because I know that it's 1. So when x equals 0, y is 1. So I can put that in. But for the rest of the numbers, for the rest of those values, I'm going to actually do things by figure them out by plugging in the x value. Because that's the best thing about a function equation is that you can plug things in. You can plug values in for x and see what you get as the output. So I'm just putting in my inputs and then just seeing what I get for my outputs. So I can basically just go down the line. I'm going to plug in a 1, see what I get. Then I'm going to plug in a 2, see what I get, and so on and so on. So let's go ahead and try that. So I'm going to start by plugging in 1. So I'm plugging in 1, and it goes into the exponent. So this is why last week we were all about exponent rules, right? Because we got to remember all of those little rules. They might come back, and you're going to see that they come back today. So I got to do my exponent. What is 2 to the power of 1?
0? Wait, no. 2.
It's 2.
2 to the power of 0, 0.
No, what's 2 to the power of 0?
That, I
1.
power of 0 equals 0.
Mm-mm,
Um,
it's 1. Matter of fact, let me show why that's true. Let me go back, hold on. If I plug in 0, I already know when I plug in 0, I'm supposed to get 1, right? Because I know that's the y-intercept. When you plug in 0, what is 2 to the power of 0 again?
1.
1. So this is 1 times
oh,
1, which is 1. If that had been a 0, Ejira, if it was a 0, if this had been 0, I would have gotten 0. But I know that my y-intercept is not 0, it's 1. So again, see what I mean? Those little rules, they do not disappear all of a sudden. They do come back in the end. So we got to keep them in mind. But anyway, I'm here. We're plugging in. We plugged in a 1. And what did we say? 2 to the power of 1 is
2.
2. 1 times 2
2.
is 2. So when I plug in when my input is 1, my output is 2. Then we go on and we're going to plug in a 2. And we're just going to keep going that way. Plugging in 2. The exponent is now a 2. What is 2 to the power of 2?
4.
4. And 1 times 4
4.
is 4. Okay. Keep going. This time I'm plugging in a 3. What is 2 to the power of 3?
8.
Good. 2 times 2 times 2 equals 8. 1 times 8 is 8. And we have this little pattern now, so we kind of get a sense of what's happening. What do you guys think is going to be f of 4 before I do the math?
16.
16. And let me just show that by doing the math. Now, obviously, I'm starting with a pretty simple example, but it's really good to just understand how to do the slightly more easy ones, because then later on, we're going to have to do it with slightly more challenging numbers. So 2 to the power of 4, 2 times 2 times 2 times 2 is 16. So we get 16. Okay, well, I've left one of these mysteriously blank. So now I got to deal with that negative. And that's where I'm going to say it again. Those rules for exponents, they do not go away. What is 2 to the power of negative 1?
1.5.
1/2. Nice job. Because what happens to this 2? Where does it go?
Denominator.
Very good. Nice job. It goes to the denominator. So we end up with 1 times 1/2. And 1 times 1/2
1/2.
is just 1/2. So I'm going to write this as 0.5. 1/2. Any questions on how I got any of those values? Awesome. Okay. So now I'm going to go ahead and graph this. And, you know, let me see if I can move this thing. Hold on. There we go. I have this graph. It actually goes up to 6 on the x-axis, and it goes up to 8 on the y-axis. So when you do your sketch of it, let me actually modify this. Let me fix that. I'm going to add a couple more lines. Okay.
Yeah, you're right.
So you're going to go up to 8 on the y-axis. So 8 lines going up. And try to make it as even as possible. Mine is not even that good, but that's okay. And then on the x-axis, it goes up to 6. So at least 6. 1, 2, 3, 4, 5, 6. And then backwards, I'm going to go a couple into the negatives as well. I'm just going to put like 2 tick marks going this way. So that's what yours should look like in your notebook. So we're just creating this coordinate grid. It doesn't have to have all those lines in the middle. We're just doing the x-axis and just the y-axis so that you can sketch it, so that you can make a graph that it might not be perfect, but at least you'll get a good idea of the shape of it and what it should be looking like. So now I can go ahead and I can put all of these values in. So I have -1, 0.5, -1, 0.5, 0, 1, 1, 2, 2, 4, 3, 8. So that 1, 2, 3, 4, 5, 6, 7, 8. So that last value, 4, 16, it's not going to fit, but that's okay because we have a lot of other points, and that already is going to give us a good idea of what the graph looks like. So now I'm just going to connect all of these dots. And then make sure that you draw an arrow on both ends of the line. All right. So as you're continuing or finishing your sketch, we're going to talk about a couple of different things that are happening in this graph. So I'm going to erase a couple of things here. And you can write this pretty much anywhere where you have a little bit of space. We're going to talk about something called end behavior. And end behavior is basically where does the arrow point? Kind of going to look at both sides of this graph, of this curved line, and we're going to explain where the arrow is going. So it's kind of different from what we've done before, but let's kind of get into it. So I'm going to look right over here at the top of this graph, because that's where one of my arrows is. And okay, where is that arrow pointing?
Up.
It's going up. Is that arrow ever going to stop?
No.
No.
No, right? So if you can think about it, what number is that arrow trying to reach? What is it going to try to reach?
Infinity?
Infinity, yeah. So over here, this is going, going towards infinity. Going towards infinity. Pretty simple, right? So what we write, because which side of the graph are we on? We are on the right side of the graph. So I'm going to write something that's going to look a little weird, but I'm going to explain it in a second. So just look carefully. This is the right side of the graph. So what I'm going to write is, as x approaches infinity, f of x also approaches infinity. So write it down, just for now, copy it into your notebook, and I'll explain exactly what this means. As x approaches infinity, f of x approaches infinity. So there's two parts to this statement, okay? It says, as x approaches infinity. That part is talking about the x-axis. Which side of the graph am I on? The right side or the left side?
The right.
I'm on the right side. On the right side of this coordinate plane, the x-axis is going towards infinity. So that's all that means. This is just telling me where to look. This is saying on the right side of the graph, so when x is approaching positive infinity, what is the function doing? We already said the function is approaching infinity. It's going up. It's going towards infinity. So on the right side of the graph, my function is going towards infinity. This is a way to write, the way that I wrote this is just, you know how in algebra, this happens all the time. In algebra, we just like to write things using letters and numbers rather than words. So this is a way of algebraically writing what we just determined, that on the right side of the graph, the function is going up towards infinity. And it might look weird, it might look a little confusing, but we're going to do this a few times today, and it'll make more and more sense the more times we do it. So if you're a little bit confused, that's okay. The most important thing is to just have this written down in your notebook so that you can refer to it later. Okay, well, that's the right side. Now let's go over to the other side and think about what's going on here. On this side of the graph, where is that arrow pointing? What is happening?
To the left.
So it's pointing to the left, right? But let's think about things as in terms of up and down. Because on the right side, it's pointing straight up, right? It's like going up towards infinity. And that's pretty obvious. But on this side, is it going up? Is it going down? Where is it going?
To the left.
Down.
It's going to the left, but at the same time, it's also going down a little tiny bit at a time, right? It's not pointing straight down, but it's also not pointing straight to the left. If you can think about it, it's curved ever so slightly downwards. And it's kind of a weird thing to think about. But what I'm going to do is I'm going to show you guys, I'm going to take a moment. I'm going to show you guys what happens if I keep going. Because right now I'm only on -1. But what actually happens on the other side of this graph, which I haven't put down yet. I haven't drawn it. So let me show you. Oh, I'm not going to install this. I'll do that later. Oh my goodness. No one look at my password. Okay. So I have this graph here. I'm actually going to put the same function into this graph. So give me 1 second to do that. So it's 2 to the power of x. Okay, here I have it. It's the same exact graph, 2 to the power of x. And what I can do with this is a really cool app because you can zoom in and zoom in super, super close, or you can zoom out really, really far. So if I zoom out really, really far, look at that. So on the right side of the graph, just like we said, this goes up forever. I could keep scrolling until the end of the world and it'll still be going up. So now let me zoom back down. Now what's happening on this side? Because we left things off over here at the -1. Notice how it is still going down. It is still going down. But what does it look like it's almost going to touch?
The line.
Yeah, the x-axis, right? It looks like it's about to touch the x-axis, but let me keep zooming in. Is it touching it?
It never touches it.
No.
It never, ever will. Even when it looks like it's about to, if I keep zooming in even further, it's not going to touch it. So let me zoom back out. See how it look like you can barely even tell that it's there. Let me make it a little darker. Okay. You can barely tell that it's there, but if I zoom all the way in as far as I can, it's still not touching the x-axis. And it never will. It never, ever, ever will. So it's kind of cool, right? It's kind of interesting. The decimals just keep getting smaller and smaller and smaller, and it's never going to reach 0. It's going to get closer and closer and closer to 0, but it's never actually going to get there. It's kind of sad, actually. Kind of sad. So what's actually happening on the left side is that it's going towards 0. It's approaching 0. It's trying to land on the x-axis, but it's never, ever going to get there. It's going to get really, really close, super, super close, but it's never actually going to touch the x-axis. It's never going to touch what you can think about it kind of like the ground. It's never going to touch the ground, 0. So on this side of the graph, now I'm on the left side. I'm on the left side. So where's my x-axis going?
To the left.
To the left. So as x approaches -infinity, that's what's happening on this side. So the way that we write this, and again, it might look a little weird, that's okay. As x approaches -infinity, f of x, the function, is approaching 0. But it's never going to get there. It's trying to reach 0, but it's just not going to get there. So that is what end behavior is. End behavior. We just wrote down the end behavior of the right side of the graph and the end behavior of the left side of the graph. And we're going to do this, like I said, we're going to do this a bunch of times today. So it does look a little bit, might look a little confusing right now, but the more we do it, the more it's going to make sense. How do we feel? Any questions? Okay, all right. So we're going to do another graph, very similar. Just like in this example, you are going to sketch it onto your notebook. That way you can see what it's supposed to look like. And we're going to be doing that a couple of times for the rest of today. Oh, no, before we do that, sorry. Before we do that, let me just explain what we just did. So this graph, the one that we just put into our notebook, is actually a very special graph. It is called the parent function for exponential functions. The parent function, in general, the parent function is like the most basic, the most simple of that type of function. So for an exponential function, this f of x equals 2 to the power of x is as simple as you can make it. Because the y-intercept, what is the y-intercept?
1.
It's 1. So the y-intercept is 1. And does it grow, does it increase, or does it decrease?
The y-intercept
The function itself, the graph.
increases.
Yeah, it's increasing. So this is a growth function, it's growing. So the reason that we call this the parent function is because the y-intercept is 1, which is the most simple number you can think of, right? 1 is very simple, very easy to remember. And it's growing, so it's going up towards infinity. This is like, if you can kind of think of it like the A+ student in the classroom. Like this is the most simple, most basic, easy to understand type of function for exponential functions. And what happens is we're going to look on the next slide that you can actually change those numbers. You can make the y-intercept bigger, you can make the growth rate bigger or smaller. You can kind of like change the way that this graph looks on your sheet of paper by changing the numbers of the function. So what we're going to do is we're going to look on the next slide at a new function, and it's going to have different numbers in it, and we're going to see what that does to the parent function. Like, how is it different from the parent function? And just to finish writing these answers here, what is the end behavior? We already wrote this down, but as x approaches positive infinity, the function also approaches positive infinity. And as x approaches negative infinity, our function is trying to reach, it's trying to reach 0. So that's the end behavior, which we already wrote down. So this is the most simple function. Now let's see what happens when we change some things about it. So take a look at our new function. What is different about this function over here?
We now have a y-intercept.
Yeah, what is the y-intercept?
3.
3. What is the growth rate?
4.
Very good. Okay, so before we graph it, can anybody try to guess what is going to look different about it? Is the growth rate bigger or smaller than the parent function?
It's bigger.
It's bigger, right? So when something has a bigger growth rate, what do you think is going to happen? Is it going to grow more quickly or more slowly?
It's gonna grow more quickly.
Quickly.
Yeah, much more quickly. So take a look at the numbers on the graph. Look at just the numbers. What do you notice about the y-axis?
That is
It's
growing.
high.
Yeah, it's going by 15s, right? So it looks like the numbers I get are probably going to be much bigger. So let's just start doing the math and let's see what happens. Now, I always like to start with the y-intercept because we already know what the y-intercept is. The y-intercept is 3. So I can just put the 3 right into my function, right into the table. And again, like I said before, copy down the table, copy down the function, and then you're going to sketch it on your sheet of paper. So when you make your graph, when you make your x-axis and your y-axis, you're going to want to go by 15s, just like they have it here. Okay. So the y-intercept is 3. Now I'm going to plug in my 1. I'll start going down, and we'll go to the -1 later. All right, so I'm plugging in 1. Remember, because of PEMDAS, I have to do the exponent first. So I have to do 4 to the power of 1. Well, 4 to the power of 1 is what?
4.
Yeah, it's just 4. And 3 times 4 is
12.
12. So here's my next value. It's 12. Then I go ahead and I'm going to plug in 2. So I'm just going to keep going down and plugging in the next number. I plug in my 2. Got to do my exponent first. So what is 4 to the power of 2?
16.
16. So now I got to do 3 times 16,
48.
which is 48. Okay. So already we can tell these numbers got real big real fast. Now going backwards, now I have to plug in my -1. And remind me, what happens when my exponent is negative?
It turns into a fraction.
Turns into a fraction. So +4 is going to become what?
1 by 12 because you have to multiply it.
Don't multiply it quite yet. So Juan, you got it. I see Juan put it in the chat. All I'm doing is bringing that 4 down into the denominator. So it's 1/4. Because now when you do multiply it, what is 3 times 1/4?
3 and 1/4.
3/4, 3/4. So 3/4 brings me to my last output value. So here it is. Here's my table. I start off real small. I start off with a fraction, but by the end of it, I'm all the way at 48. And that is how these things go. These guys, they grow really, really fast. So I'm going to go ahead and I'm going to plot these points down on my graph. Like I said before, do your best to sketch the graph. It does not have to be perfect, but just make sure. Oh, and Juan, yeah, I'm going to make this 0.75. Thank you. It's just easier to graph it that way. And make sure that when you're making your graph, the most important thing is to have the right shape, even if it's not hitting exactly the perfect numbers. Just make sure the shape is correct. So here we go, -1, 0.75. Well, that's tiny. That's really close to the x-axis. Then I have 0.3. Again, that's somewhere down here. 1.12. Somewhere over here. And I'm also kind of estimating where it goes. And then 2.48. That'll be somewhere up there. So the shape, like I said, the shape is the most important thing, even if your dots are not perfectly in the right place. There it is. All right. So go ahead and just do your best to sketch that graph. I'll give you guys a little bit more time. And then start thinking about those last 2 questions that I have. Is the function growing or is it decaying? And then think about the end behavior of the graph. Okay. So as you finish your sketches, let's think about, first of all, is this growing or decaying?
Growing.
It's also growing. Good. And now let's actually think about, let's compare this to the parent function. So I'm just going to go back for a second and take a look at the parent function compared with our function. Is the end behavior the same or different?
Same.
Yeah, it has the same exact end behavior because it didn't change in any way other than becoming a little bit more steep. Since the growth rate is bigger, the graph grows faster, but it's still going to the same two places. So I'm going to write it again. So as x approaches positive infinity, so on the right side of the graph, as x approaches positive infinity, the function, our function, is also approaching positive infinity. So as x approaches positive infinity, f of x approaches positive infinity. On the other side, as x approaches negative infinity, so on the left side, where's our function trying to go but never going to reach?
0.
0. F of x approaches 0. So that is my end behavior, and it's exactly the same as the parent function. It's exactly the same. All right. How do we feel? Any questions at this point? Does anyone still need a moment on this screen, or can I move on? Okay, so I'm going to go ahead and move on. Okay, now let's take a look at this one. Before I graph it, before I do anything, let's just see the difference between this function and the parent function. So what is different now?
There's a decimal for the growth.
Yeah, the growth rate is a decimal now. So what is the y-intercept?
2.
2. And the growth rate is now a decimal. So that's probably going to change some things, right? Since it's a decimal, what are some predictions? What do you guys think might happen?
It will decay.
It might actually end up decaying instead of growing. That's a very good guess. So let's take a look at what happens. The best way to find out is by plugging in those numbers and then putting them on your graph. So my y-intercept is 2. I'll start by putting that right into my table. And then we're going to go ahead and plug in a 1. Plugging in 1. Now for this example, you can definitely use a calculator, okay? So definitely you may use a calculator because we have decimals and I don't expect you to do that by hand. You are allowed to use a calculator. So first thing I gotta do is the exponent. Well, what's 0.4 to the power of 1?
0.4.
Just 0.4. And what's 2 times 0.4?
0.8.
0.8. 0.8, okay. Then I'm gonna go ahead and I'm gonna plug in my 2. F of 2. Now I gotta use my calculator, and what is 0.4 to the power of 2?
0.16.
0.16. So Juan, be careful because it is still a decimal. It's 0.16. Then we multiply 0.16 times 2 and we get
0.32.
0.32. Okay. just by looking at the pattern, what seems to be happening?
It's growing, but at a slower rate.
So is it growing? Juan says it's decaying. Do we agree?
Oh, I'm sorry. I was going from the top to the bottom instead of from the bottom to the top.
Okay,
Well, but
so what happens as you go down? 2, then you go down, you get 0.8, you go down, you get 0.32. Those numbers are getting smaller and smaller and smaller. So it is decaying. It is decaying. So when I plug in -1, what do we expect to get?
Negative.
Okay, let's see what happens. So I'm plugging in -1. Like I said, you can use your calculator. What is 0.4 to the power of -1?
Negative 0.4.
2.5.
Remind me again, what happens when you have a negative exponent? What happens to the number itself?
It becomes a positive. Well, no, it becomes
Zero.
It becomes a fraction.
It becomes a fraction. So the 0.4, where does it go?
on the denominator.
To the denominator. So this is now 1 over 0.4. 1 over 0.4. Go into your calculator and plug in. You can use your calculator. What is 1 divided by 0.4?
2.5.
2.5.
2.5. So does it become negative? Oops.
No, it becomes a positive.
It becomes a bigger number. So be very careful with negative exponents because it happens to everybody. It happens to me. It happens, and I'm sure it's happened to each and every one of you. A negative exponent doesn't turn your value into a negative. It turns it into a fraction. Okay, so just make sure that we're continuing to understand that, and just something that it trips everybody up because it's a little bit weird, but very important. So finally, when I multiply 2 times 2.5, what do I get? Two times 2.5.
5.
I get 5. 5. And okay, so Juan is saying already it's the opposite of a parent function. I like the way you think, Juan. So let's take a look. Negative, okay, and then again, when you graph this, when you sketch this on your graph, on your sheet of paper, do your best. It does not have to be perfect, but at least get the right shape. So -1 comma 5, 0 comma 2, 1 comma 0.8, that's going to be somewhere around here, and then 2 comma 0.32 gets closer and closer to 0, but it's never going to really get there. And there's my graph. Not perfect by any means, but like I said, that's okay as long as you get the general shape of it. Because now, like Juan just said, this is not the same as the parent function anymore. It kind of is the opposite. So the end behavior is going to be different, which we'll talk about in just a second. So in this case, is it growing or decaying? What's happening?
Decay.
It's decaying, yeah. It's decaying. And now the end behavior, since this is kind of the opposite of the parent function, the end behavior is probably also going to be the opposite. So let's just take a look. On the right side of my graph, as x approaches infinity, where is the function going?
To the to the left.
On the right side.
Right. Oh.
Where's this function going, but never really going to touch?
Negative? No, there's no such thing as -0.
Actually, Juan, I see it posted it in the chat. As x approaches infinity, f of x is trying really hard, but it's never going to touch the ground. It's never going to get to 0. So it's approaching 0.
It's still gonna be 0 then.
Right. Think of it like a plane landing. Like it's a plane will touch the ground. This function is kind of like a plane that's landing, but never going to actually touch the ground. Now, on the other side of things, as x approaches negative infinity, where's our graph going? F of x. As x approaches
Back
negative.
to infinity.
Good. We are going to infinity and beyond. So there's our two end behaviors. Let me write them down over here. So as x approaches infinity, f of x is approaching 0. As x approaches negative infinity, f of x is approaching positive infinity. Now, when we're writing end behavior, this part is always the same. Because that part, the x approaching infinity and the x approaching negative infinity, is just telling me to look on the right side of the graph and then telling me to look on the left side of the graph. So you'll notice that that is always going to be the same, what I highlighted in blue. What changes is what the function is actually doing, because sometimes, like we saw in the previous example, this is the same. It can be facing one direction like it is here, or it could be facing the opposite direction like it is here. So it's important to be able to explain what is happening on the graph using this type of notation. Juan, you're reading the future. That's not fair. You're cheating. How did you know? Okay. But any questions on this one? Any questions on this graph? Anything at all?
Will we be dealing with a negative growth rate?
I don't know. Will we?
Called it.
Juan called it first, technically. Well, okay, but let's actually think about it. Is the growth rate negative or something else is negative?
The y-intercept.
The y-intercept is negative. So to answer your question, Ajira, the growth rate will never be negative in any of these examples. Only the y-intercept might be negative, but the growth rate itself, it mathematically can't be negative. And we'll kind of talk about that at the end of today, but I'll explain why that is in a little while. But for now, let's just keep going with what we're doing. This time, the y-intercept is negative, right? This time, the y-intercept is negative. So the y-intercept is -3. The growth rate is +4. So this one's a little bit similar to example 2, where I had +3 and +4. Now I've got -3 and +4. So let's see how that changes things.
We just have to put the other, like the answers that we had before for this equation, for this equation as a negative instead, as a positive.
So it looks like maybe all of our answers will be the same numbers, but negative. Let's double check. I think you might be right, but let's double check. So my y-intercept is -3. And same as before, we're just going to go ahead and start plugging things in. So to the power of 1, what do I get here?
-12.
Yeah, -12, because I've got -3 times 4, which gives me -12. Then I plug in negative, or yeah, I plug in 2. What happens here?
Negative 48.
Negative 48, yeah. So it looks like Ejiro was right. All of the numbers are basically the same, but negative, right? Because this time the y-intercept is negative, so each time I multiply, I'm multiplying by -3 rather than +3, which turns all of my answers into negatives. So now, last one, plugging in -1. Remind me one more time, and it's gonna get repetitive, but it's just because I want to make sure we understand what happens with a negative exponent.
Turn into a fraction.
Turns into a fraction. So +4 becomes
4.
1
1 over
over
4.
4, yeah. And then -3 times 1/4.
Negative 3/4.
-3 over 4, yeah. Turned into a decimal, that's -0.75. Okay. Now, before I graph it, take a look at the patterns. Is this function growing or is it decaying?
Decaying.
Decaying.
It's getting more and more negative each time, right? So even though the numbers are getting bigger, technically, right, 3, 12, 48, since they're negative, what that means is it's actually getting lower and lower. So it is decaying. So now let's take a look at what the graph will look like. -1, -0.75, 0, comma, -3, 1, comma, -12, and 2, comma, -48. Okay. There it is. So, like we determined, this is definitely decaying. It's going down. And what does this kind of like, what's the difference between this graph and the parent function? So I'm gonna go back to the parent function for a second. How would you describe what happened between this one and the one we have here?
The one we have here is going down instead of up.
Right, it's totally, there's a word I'm thinking of. I don't know if anyone's gonna say it, but there's kind of a transformation that happens. It was going up, now it's going down. It's going up. Now
It
it's
just flipped.
flipped. There it is. You got it. So it's flipped. Juan says reversed. Kind of similar, but the idea of flipping, it's kind of like it used to be. I'm going to draw the parent function in blue. It used to look something like this, right? Where it was going upwards. This flipped downwards. It's like it flipped like a book, like over the x-axis, because of that negative sign in the front. That negative sign basically turns the entire thing backwards. It turns it upside down. So it's flipped. So now let's think about end behavior. On the right side, as x approaches infinity, where's our graph going now? Where's f of x going?
Negative infinity.
Negative infinity, exactly. Right, because there's positive infinity when you go up, there's negative infinity when you go down. And as x approaches negative infinity, where is the function going?
0.
0.
Good. Good, good, good. See, it kind of starts making a little more sense the more you do it. All right. So to sort of summarize everything so far, we have seen a positive increasing graph. So it's just positive going up. Everything's nice and happy. This is growth. We've seen a positive decreasing graph, so it's decaying, going down, but it's still on top of the x-axis, above the x-axis. And now we've seen a negative decreasing graph, which is all below the x-axis and going down. So what do you think is left? We got one more. Now we have a negative increasing. So let's take a look at the difference. Now what's happening here? We have everything's different. What's the y-intercept?
-3.
Okay, so our y-intercept is still negative, but now the growth rate
It's a decimal.
is a decimal. So we have a negative y-intercept and a decimal. So things are going to look a little bit different now. What do you guys think? Is this one going to grow or decay?
DK.
Decay, because what was happening here? This one was decaying, but what was the growth rate?
A positive.
Ooh, okay. So it was a positive growth rate, but it ended up decaying. Why was that?
Because a negative times a positive equals a negative.
Right. So since the y-intercept was negative and the growth rate was positive, it ended up decaying. Well, now the y-intercept is negative. The growth rate is a decimal. So let's see what happens. Let's find out. So my y-intercept is -3. And same as before, we're just going to go ahead and plug everything in.
I was going to plagiarize from our last, okay, never mind. It was a 2. Darn.
From when we did it with the +3?
Yes. No, with the +2.
Oh, yeah. Okay, because it was a 2 before. All right, so now 0.4 to the power of 1
0.4.
is 0.4. What's -3 times 0.4?
Wait. 0.12. -12. No, -0.12.
You got it. Good. -0.12. Okay.
Oh, wait, we don't have to use our calculators. This isn't half bad.
It's not terrible. Okay. 2. F of 2. 0.4 to the power of 2.
16.
And it's 0.16.
Oh, sorry, 0.16.
-3 times 0.16.
-0.48.
-0.48. Good. All right. Question so far. Cool. Sorry, I just realized there was a small mistake. It's not -0.12, it's -1.2. I multiplied that wrong in my head. Okay, now going backwards, plugging in my -1, we know things are going to be a little bit weird. What happens when you have a negative exponent?
Turn
What?
into fraction.
Turns into a fraction. So I have 1 over 0.4. What is 1 divided by 0.4?
2.5.
2.5. Good.
2.5.
So what is -3 times 2.5?
-6.
You're close.
-5.
That's 2 times 2.5.
Oh,
We're doing 3 times 2.
-7.
Negative, not just 7. You can use your calculator.
7.5.
-7.5.
There you go. Look at All y'all trying to do this in your head when you have your calculators right in front of you. Negative 7.5. Okay, so before I graph it, what's happening with these numbers? They're becoming less and less.
Positive. No, it's decaying.
There is, yeah.
So are the numbers getting bigger or are the numbers getting smaller?
No, it's getting bigger
Why bigger?
because
Oh, okay. I see it. I
if
understand.
it's a negative, like if it's like the least number is actually greater.
Yeah. Yeah, because what's really happening is they're becoming less and less negative. So on my number line, they're actually going closer and closer to zero. So they're going up. So these numbers are actually increasing. But it's kind of weird, right? Because they're negative. So it's kind of hard to understand that. So let's just graph it. Let's see what that actually looks like. Negative 1, comma, negative 0, negative 7.5. It's actually right here. Nice. 0, comma, negative 3. 1, comma, 1.2. And then negative and 2 comma negative 0.48. So there it is. So this is the last like kind of direction that things can be pointing in, because we've seen all four possibilities. We've seen it going straight up, we've seen it coming down, we've seen it flipped over. Now this is like flipped, double flipped. So is this one growing or is it decaying?
Growing.
Yeah, it's actually growing because it is increasing. It is going up. It's just that since we were on the negative side of things, it's kind of like weird. It's kind of backwards in your head. And now end behavior. On the right side of things, as x approaches infinity, what's happening to my function? Where's f of x going?
Negative infinity or positive infinity? No, 0.
Zero.
Yeah.
Yeah. It's trying to reach that x-axis, but it's never going to get there. Well, on the other side of things, on the negative, x approaching negative infinity, where's my function going here?
Negative infinity as well.
Negative infinity as well. So now I've got my two situations. As x approaches infinity, f of x approaches 0. And as x approaches negative infinity, f of x approaches negative infinity as well. And like I said before, this part of it doesn't change. It's always the same as x approaches positive infinity and as x approaches negative infinity. That's just indicating that I need to look on the right side of the graph and then I need to look at the left side of the graph.
Oh, so it all depends on which side it's going down from or up from.
Yeah, so basically, let me actually flip back a couple. So let me just go back to the first one we did. I highlighted it in blue because that's just helpful for visualization. But when I'm writing end behavior, remember, okay, actually, let me go back even more. When I'm writing end behavior, I'm always asking, where does the arrow point? Is it going up? Is it going down? Or is it going to 0? Those are always your only three options. You're either going up to positive infinity, going down to negative infinity, or going to 0. And in the parent function, a normal positive graph like this one, the right side approaches infinity, the left side approaches 0. So as x approaches positive infinity, so this is the right side, on the right side, the graph goes towards infinity. On the left side, the graph goes to 0. So that's what I highlighted in blue, that's what that's telling you to look at. It's telling you to look on the right side as x approaches infinity, and it's telling you to look on the left side as x approaches negative infinity. So that's why those two statements never change. It's always going to say x approaching infinity and x approaching negative infinity. And what you have to fill in, kind of like fill in the blank, is just this part right here. It's just, where is the function? Where is the function pointing? Is it pointing up? Is it pointing down? Or is it going towards 0? So that's always what we were filling in for each of these. All right. Okay. So we've done 4 graphs. It's 10:38, so I kind of want to finish here, but I do want to give you guys one sort of like test problem. I don't know if I have one here though. I don't think I do. Okay, I don't. That's okay. What we're going to do tomorrow is kind of pick up. I didn't want to do all of this today because the next couple of graphs are a little bit different, but we'll pick up with that tomorrow. So at this point, what I want to do, because there's 5 minutes left, is I just want to open the floor for any questions you guys have. And or what you guys can do in these last 5 minutes is go onto Khan Academy and take a look at the assignments that I've posted if you haven't done them yet, just to kind of start on it and see what they look like and see if there's any questions you might want to ask me right now while I'm here. So last 5 minutes are just questions / start the homework assignment to see what it's all about and see if you have any questions.